Hey everyone, and welcome to another deep dive. Today we're diving headfirst into the world of chemical reactions.
Yeah, those fascinating interactions that make chemistry so
You
dynamic.
know, the kind that makes things fizz and pop and sometimes even heat up.
Exactly. And we're going to visualize one of these reactions using this really cool online simulation.
Oh wow, I love a good visual.
It's like watching a tiny invisible dance party of molecules.
Okay, color me intrigued. So what reaction are we looking at?
It's hydrogen H2 reacting with bromine, Br2, to form hydrogen bromide, HBr.
Ah, hydrogen and bromine. Those names take me back to high school chemistry class.
And you know what's really cool about this reaction?
What's that?
It's reversible.
Reversible, so it can go backwards.
Exactly. The hydrogen bromide can break back down into hydrogen and bromine.
Huh, so it's a two-way street.
Yeah, and that's going to be important when we talk about equilibrium later on.
Okay, got it. Reversible reaction.
Yeah.
You're making a note of that. The source also mentions that this reaction is exothermic.
Oh, yes, that's a key piece of information.
Does that have anything to do with those hand warmers that heat up when you activate them?
Yes, you're exactly right. Exothermic reactions release heat, just like those hand warmers.
Oh, cool. So it's like the molecules are throwing a little party and giving off heat as they rearrange.
Yeah, I love that analogy.
So we've got these hydrogen and bromine molecules getting together to form hydrogen bromide. What do they actually look like in the simulation?
Well, the simulation uses different colors to represent each molecule.
Oh, that makes it easy to follow. So what are the colors?
Hydrogen molecules, H2, are shown as white particles. Bromine molecules, Br2, are red. And the hydrogen bromide, HBr, that's formed is green.
Okay, so white, red, and green. It's like a little molecular traffic light.
Haha, I like it.
Are all these molecules the same size, though?
That's a great question. They're actually not.
Oh, really?
The source gives us the atomic masses, which tell us how much each atom weighs, and it turns out bromine is a lot heavier than hydrogen.
Wow, so it's like a dance floor with some lightweight dancers, the hydrogen, and some real heavyweights, the bromine.
I love that visual.
So we've got these molecules of different sizes zipping around and bumping into each other.
Right, and those collisions are where all the action happens.
Okay, so when they bump into each other with enough energy...
They can break apart and rearrange themselves to form new molecules.
So that's how the reaction happens.
Exactly.
I'm starting to get a picture of this invisible dance party in my head.
Yeah.
But you mentioned equilibrium earlier. What exactly does that mean in this context?
Well, imagine our molecular dance floor. At the beginning, you have mostly hydrogen and bromine molecules dancing around, colliding, and forming some hydrogen bromine.
Okay, so lots of red and white at the start with a bit of green appearing.
Right. But remember, this reaction is reversible.
Right, it can go both ways.
So as more hydrogen bromine forms, those green molecules can also bump into each other
Okay.
and break back down into hydrogen and bromine.
Got it. So it's like a two-step dance forward and backward.
Exactly. Hydrogen and bromine come together to form hydrogen bromide,
Yeah.
and then the hydrogen bromide can split apart again.
So what happens then? Does it just keep going back and forth forever?
It does. But here's the fascinating part. Eventually, this dance reaches a point of balance.
Balance? You mean like everyone just stands still?
Not exactly. It's more like a dynamic balance. The forward reaction and the reverse reaction are both happening, but at the same rate.
So it's still moving and grooving, but the overall number of red, white, and green molecules stays pretty much the same.
Precisely. And we call this state of balance change equilibrium.
Okay, equilibrium balance change. It's making sense. Now, how do we know when this equilibrium point has been reached? Is there like a signal or something?
Well, scientists use something called the equilibrium constant to measure the ratio of products to reactants at equilibrium.
So it's like a snapshot of the dance floor at that moment of balance.
Exactly. It tells us how many of each molecule are present at equilibrium.
But hold on, is this equilibrium constant fixed or can it change?
That's a great question, and it's something we'll be exploring more in the next part of our deep dive.
Okay, I'm definitely curious to hear more about that. But for now, let's recap what we've learned so far. We've got this reaction, hydrogen plus bromine, forming hydrogen bromide.
Right.
And it's a reversible reaction, so it goes both ways,
And eventually it reaches a state of dynamic balance called equilibrium.
where the forward and reverse reactions are happening at the same rate.
And all this is happening at a molecular level with these tiny particles colliding, breaking apart, and forming new bonds.
It's like a whole world of activity happening in a test tube. It's
Yeah.
really fascinating. But why should we care about this invisible dance party?
That's a fantastic question, and it's something we'll be digging into in the next part of our deep dive.
Okay, I'm hooked. I can't wait to find out more. Stay tuned for part 2 of our deep dive into the world of chemical reactions and equilibrium.
Welcome back to our deep dive into chemical reactions. We've been looking at this reaction between hydrogen and bromine and talking about how it reaches this state of equilibrium. But there's another key player we haven't talked about yet, energy.
Oh yeah, energy, that makes sense. It takes energy to make things happen.
Exactly. Like, you need energy to get going in the morning. Chemical reactions need energy to get started.
Right, like I need my coffee to function.
And remember we talked about this reaction being exothermic?
Yeah, it releases heat like those hand warmers we were talking about.
Exactly. And that heat, that's a form of energy. It's being released because of changes happening in the energy stored within the molecules.
Okay, so where is this energy stored?
It's all about the bonds that hold the atoms together in a molecule.
Bonds. Are we talking like James Bond?
Not quite. Though chemical bonds can be pretty exciting too. Think of it this way. Each molecule is like a little group of atoms holding hands.
Okay, I'm visualizing it.
And to break those bonds, you need to put in some energy.
So it's like convincing those atoms to let go of each other.
Precisely. Breaking bonds requires energy.
Got it. What about forming new bonds?
Forming new bonds is the opposite. It actually releases energy. It's like when those atoms find new partners and hold hands again. They release a burst of energy as they settle into their new arrangement.
So it's a trade-off, energy in air, to break bonds, energy out to form bonds.
You got it. And the difference between those two amounts of energy determines whether a reaction is exothermic, like our hand warmers, or endothermic.
Endothermic being the opposite, where it absorbs heat.
Exactly.
So how do we actually measure this energy difference?
That's where bond energies come in. Scientists have actually measured how much energy is involved in breaking and forming different types of bonds.
Wow, so we know exactly how much energy it takes to, say, break a hydrogen bond or form a hydrogen-bromine bond.
Exactly. And for our reaction, the energy that's released when we form two HBr bonds.
The hydrogen-bromine bonds.
Right. That energy is greater than the energy we need to break the initial H2 and Br2 bonds.
The hydrogen and bromine bonds.
Yeah. So overall, there's a net release of energy, and that's why this reaction is exothermic.
Yeah. Okay, so all that heat we were talking about, that's just that extra energy being released because the new bonds are more stable energy-wise.
Exactly. The molecules are settling into a more comfortable, lower energy arrangement.
That's really cool. So how does this energy stuff relate back to equilibrium? We talked about it being a state of balance. Is there a connection?
There is. It turns out that equilibrium is not only a state of balance in terms of concentrations, but it's also a state of minimum energy.
Minimum energy. So are the molecules like relaxing on the dance floor?
Haha.
Yeah.
In a way, yeah. At equilibrium, the system has found that sweet spot where the energy of the reactants and products are in balance.
Got it. So if we disrupt that balance like we were talking about before by changing the temperature, what happens?
Well, if we add more energy to the system by heating it up, that's going to shift the equilibrium. Remember, changing the temperature is like turning up the music at our dance party.
Right. Everyone starts moving faster and maybe switching partners more often.
Exactly. And that extra energy might favor one direction of the reaction over the other.
So it's like the system is trying to find a new equilibrium point to adjust to this new energy input.
Precisely. It's a constant push and pull between energy and equilibrium. And understanding this is key to understanding how chemical reactions work in the real world.
Okay, that's amazing. So we've gone from thinking about these tiny molecules to this whole concept of energy and equilibrium. It's incredible how much is going on in a seemingly simple chemical reaction.
It is. And you know what? The specific reaction we've been looking at, hydrogen plus bromine, it actually has some interesting real-world applications.
Really? Like what?
Well, did you know that hydrogen bromide is used in the production of some pharmaceuticals?
No way.
Yeah, and it's also used in some flame retardants.
Wow. So this reaction we've been visualizing, it's actually used to make things that impact our lives.
Exactly. And it's all because we understand these principles of chemical reactions and equilibrium.
Okay, that's pretty mind-blowing. I have a feeling there's even more to the story though, right?
You're absolutely right. We've been focused on this one specific reaction, but these concepts like equilibrium and energy changes, they apply to tons of reactions happening all around us all the time.
So it's like we've been learning this secret language of chemistry.
And now we can start to see how it's used in different contexts.
Awesome. So where do we go from here?
Well, in the final part of our deep dive, we're going to zoom out even further and look at some of the real-world applications of equilibrium in fields like biology, environmental science, and even industry.
Oh, wow. Okay, I can't wait to hear about that.
Yeah.
But for now, let's recap what we've learned about energy and equilibrium today.
Okay, great idea. We saw that breaking bonds requires energy,
Uh,
and forming bonds releases energy.
right.
And that difference in energy determines whether a reaction is exothermic or endothermic.
And we also learned that equilibrium isn't just a state of balance, but it's also a state of minimum energy.
Right. The system wants to find that sweet spot where the energy of the reactants and the energy of the products are in harmony.
And if anything changes, like the temperature, that can disrupt the balance and cause the equilibrium to shift.
Exactly. It's all interconnected, and we'll see just how far-reaching those connections are in the last part of our deep dive.
Okay, I'm really excited for that. Stay tuned, everyone, for part 3 of our deep dive, where we explore even more about the fascinating world of chemical reactions and equilibrium. We're back for the final part of our deep dive. I'm so excited to hear about these real-world applications of equilibrium. You mentioned biology, environmental science, and industry. Where should we start?
Well, let's start with something we can all relate to our own bodies.
Okay, so biology it is.
Think about all the incredible things happening inside you right now. Breathing, digesting, even thinking.
Yeah, it's pretty amazing when you think about it.
It's all chemistry in action.
So basically, we're just talking chemical reaction.
In a way, yeah. And so many of these biological processes rely on equilibrium to work properly.
Okay, I'm curious. Tell me more.
We'll take enzymes, for example.
Enzymes, those are like those tiny helpers that speed up reactions,
Mhm.
right?
Exactly. They're like little molecular machines that make sure reactions happen quickly and efficiently.
I remember learning about enzymes in biology class, but I never really thought about them in terms of equilibrium.
Well, enzymes often create this microenvironment where reactants and products can reach equilibrium faster.
So they're like setting up the perfect dance floor for our molecular party.
I love that analogy. And this careful control of equilibrium is essential from maintaining homeostasis.
Homeostasis. Remind me what that is again.
It's basically the stable internal environment our bodies need to function properly. Keeping everything in balance.
Ah, yeah, like keeping our temperature stable and stuff.
Exactly.
Wow, so equilibrium is literally keeping us alive. That's incredible.
Yeah.
What about environmental science? How does equilibrium play a role there?
Well, one of the biggest examples is the balance of carbon dioxide between the atmosphere and the oceans.
Oh yeah, the carbon cycle. I've heard about that.
Exactly. There's this natural equilibrium between the CO2 in the air and the CO2 dissolved in the ocean.
Right.
But human activities like burning fossil fuels, they're releasing way more CO2 into the atmosphere.
And that's what's messing with the climate, right?
Exactly. We're disrupting that natural equilibrium of the carbon cycle. It's like we've overloaded one side of the seesaw and the whole system is trying to rebalance.
So it's not just individual reactions reaching equilibrium.
Mm-hmm.
It's about whole systems trying to find that balance.
Precisely.
Okay, that's pretty mind-blowing.
Yeah.
What about industry? How is equilibrium used there?
Well, a lot of industrial processes involve manipulating equilibrium to produce specific products.
Really?
One classic example is the Haber-Bosch process. It's used to make ammonia.
Ammonia. Isn't that like a cleaning product or something?
It's used in cleaning products,
Yeah.
but its main use is actually in fertilizers.
Fertilizers, the stuff that helps plants grow.
Exactly. And the Haber-Bosch process is actually responsible for producing a huge amount of the world's fertilizer.
Wow. So this one chemical reaction based on the principles of equilibrium is helping to feed the world.
It is, and it all comes down to understanding how to shift the equilibrium to favor the formation of ammonia. By tweaking things like temperature and pressure, chemists can optimize the process.
So it's like they're fine-tuning the conditions to get the best results.
Exactly. And this same principle applies to countless other industrial processes, making plastics, pharmaceuticals, even developing new energy technologies.
Wow. I never realized how important equilibrium is. It's everywhere.
It truly is. It's a fundamental principle that governs so many processes, both big and small.
It's really changed my perspective on chemistry. You know, we started with this simple online simulation.
Of hydrogen and bromine reacting.
Yeah, and look how far we've come. It's amazing how exploring one specific example can lead to so much understanding.
It really shows the power of scientific inquiry.
Absolutely. We've learned about bond energies, the factors that affect equilibrium, and how scientists and engineers use this knowledge to create all sorts of amazing things.
And it all comes back to that double arrow, the symbol of reversibility, the reminder that these reactions are dynamic and always trying to find balance.
It's amazing to think that even though we can't see these tiny molecules, they're constantly interacting and shaping the world around us.
And by understanding the principles behind those interactions, we can gain a deeper appreciation for the incredible complexity of the world.
Well said. I think we've definitely reached equilibrium in terms of our knowledge today. Thank you so much for joining us on this deep dive. We hope you've learned something new and maybe even gained a newfound appreciation for the invisible world of chemical reactions.
And remember, stay curious. There's always more to explore and discover.